This is our 11th week, and to this point we have covered several of the topics related to the interplanetary trajectories, and today hopefully we shall be finishing our math model and the solution that we are building for one of the case studies of the Venusian mission, so that thereafter you can do your own design calculations, mission design calculations. To this point, what we have done, I'm just going to quickly repeat those items. We have finished this point, the calculations of the sphere of influence. Then we started off with the basic and a very simplified calculations, which was related to the simple Hoffman transfer, which was from the ideal location, which is actually the the two planetary positions lying at opposite apses. And then we calculated the synodic periods for different planetary bodies. Thereafter, we went for the trajectory calculations, and the trajectory calculations led to the development of the PC plot, which is and this was able to give us the value of the C3 and the variation of our type 1 and type 2. And there was a lot of mathematical model that ultimately culminated into this, the pork-chop plot. After that, there was to do this thing, we had to first develop the position of the planets according to the solar dates as well as the Julian dates, and then from there onwards we used the ephemeride services of JPL, for example, to calculate, to determine the ephemerides of the planets on the dates of departure and arrival. This was all done to basically start the calculation for the PC plots. And then once that was done, after that we did the planetary elements calculation, completed the planetary orbital elements calculation, which was the true anomaly and the velocity and the flight path angle of the planet at the departure and that of the arrival. Once we had the time of flight determined from the difference between the travel time between the departure date and the arrival date, so then we carried out a trial and error method. The trial and error method was to fit the transfer ellipse such that it would have it would meet the requirement of the TOF required, which was the time of flight between the departure from one planet and arrival at the other planet at the sphere of influences. So this calculation was done. And then we did the departure trajectory in the last lectures, and in which we did the design of the plane change. The plane change that was gave us a spherical triangle, and the spherical triangle then would help us solve for the inclination that was required from the Earth on its transfer to the transfer ellipse. And to get into that transfer ellipse, this is now this solution was being solved inside the sphere of influence. So we were inside the RSOI, and which was actually a hyperbolic trajectory calculation. So all these were performed, and it was the most important thing was the calculation of the hyperbolic excess velocity, the VHE excess velocity, and the third cosmic energy. And then we were able to calculate based on this check for the matching of the arrival dates on the chop plots, and see if we were able to match the results were matching with the chop plots data for the type 1 or type 2 trajectory, whatever was applicable. We also calculated the burnout velocity. We also determined the size of the hyperbolic orbit, as well as the angle of the change of the asymptotes. And then of course we were able to also determine, as per the azimuth, the maximum and the minimum azimuth that was required according to the rotation of the launch port. Now today what we'll be doing is we're going to put together based on all that we have done, we will be doing the arrival trajectory calculation, and for that we'll be using a B-plane method. And then the rest of the calculations will follow the same method of the design of plane change, which will give us, just like an ITE on the Earth side, it will give us the ITV on the Venusian side. It will also give us the measurements, the magnitude of the V infinity, which is the velocity at the infinite location, and this C3. And after that we are going to do gravity assist maneuvers and make some variations to this gravity assist maneuver in terms of the maximization of the velocity as well as the maximization of the turning of the spacecraft inside the gravity assist, because now this solution. So basically the step number 14 to 17 and onwards, this is all inside the RSOI of the Venus, whereas the previous tests were all, the departure tests were all inside the RSOI of Earth. And prior to that, all the calculations were done outside the RSOI of both the planets, but within the gravitational field of the Sun in the solar system. So let's start with the design of the arrival trajectory. Now this design of the arrival trajectory is done by a method. There are several methods to do this, but the one which is, as we say, very common is called as the B-plane. And why do we do this? So the arrival trajectory, the reason we are doing the arrival trajectory is, first of all, we want to get to the target planet. But why do we wish to get to the target planet? Generally, one reason is that we want to create a direct impact. For example, you impact a satellite onto the surface of a planet to see what is composed of the surface itself and how does the impact occur. So there are many spacecraft that do that, which are bombarded. For example, the Ranger spacecraft was bombarded onto the Martian surface. Then we had so many other spacecraft, and many of the rovers also do this at the end of their lives. So either you make a direct impact onto the planet, or you want to use the planetary gravity assist to move onwards for an interplanetary motion. So for example, you get out of the Earth's orbit, get into the Venus orbit, and it uses a flyby of the Venus, and then you go on to another orbit and to another planet, and so on and so forth. You keep moving. For example, the Voyager's mission uses spacecraft, different planetary bodies to hop from one planetary body to the next planetary. So that is called as a gravity assist. And the third is called as a planetary probe. So you enter a planetary orbit and you stay in that orbit, and that could actually mean, if you have a probe, you can also have some kind of a lander also, which can just go on to land, and using either the astronauts or some kind of rovers. So with this lander you can take the astronauts there, or you can take the rovers, and so on and so forth. But the primary thing is that you have to bring the probe in. This probe is actually a remote sensing system. So it's a remote sensing satellite which is now orbiting inside the orbit of that particular target planet, and so it's staying there. So there are three different reasons why we do that. And there's so many of these probes that we have. We have Chang'e 4 and 5, which are in the moon. We have Magellan, which is in Mars. Then we have the NASA probes that are in Mars, and then we have Juno, which was in Jupiter's orbit, and so on and so forth. So the point is that we have to do this by creating something called as an arrival targeting. So arrival targeting means that you are going to target a particular planet, then you're going to arrive in that planet with the particular aim which is listed here. So these three things, these three types primarily are your objectives, and so that will determine how you're going to make an entry into the B plane. Now what exactly is a B plane? Basically what happens is that we are placing an incoming asymptote in the desired location relative to the target plane, and so let's do that. Let's do that by drawing it, and we need to draw a couple of figures here. So let's suppose this was our target planet, okay, and it's at a certain angle, which is usually true for almost all the planets. So they are let's say they have a certain orbital plane, and this orbital plane also contains the motion of the incoming spacecraft. So we have this plane of this planet, and this plane also holds, because once the incoming spacecraft has arrived into the planet's orbit, so it is in the same plane as the target planet. So let's suppose this is our incoming spacecraft. It has arrived into the same plane. So the host planet as well as the spacecraft, and let's say this plane is aligned with the equator of this target planet. Now, what we do is, in order to determine how this what should be the distance between the spacecraft and the host planet, depending on the three aims that we have set, we are going to make a orthogonal interception plane, which is called as the B plane. So we're going to make an orthogonal intercept plane here. So let's make it here. So because this is at an angle, so let's say this is slightly at an angle, and that's my intercept B plane. So I make a plane which is at 90 degrees to the orbital plane housing the spacecraft. So let's mark these plane. This is the horizontal plane, and this of course would be our vertical plane here. So both are at 90 degrees to each other. Okay, let's finish this. Okay, so what happens is, if I project the position of my satellite, of my host planet here, so this is the direction of the propagation V infinity. Why it is the direction of V infinity? It's because we have a V infinity of the satellite or the spacecraft, which we are also passing through the same center of the motion of the central body around which the spacecraft is moving. So this is the direction of the V infinity of the spacecraft, and we pass it because we have to create a hyperbolic trajectory. For that, the V infinity has to pass through the center of the central body. This is the basic construct of a hyperbolic trajectory. So I am passing this here, and I can project the surface of this planet onto the B plane. So my B plane is orthogonal. So what happens is that this same surface is now shifted 90 degrees. So I will see this surface here in 90 degrees in this manner. So that's my surface. So let's just highlight this. Okay, and this has a orbital radius, let's say r0, which is projected onto the plane. And now let's bring the spacecraft in. So the spacecraft comes in and along a hyperbolic trajectory, and so at this point it becomes parallel to the V infinity. So this is the V infinity, and this has it crosses the B plane at this location. We can give it a number or something, but this is the position of the crossing of this B plane. Now, in order to determine whether it's an impact spacecraft or a gravity assist, will determine how much is the distance between the spacecraft and the surface of the planetary body. So let's project now the path of the planetary body. Let's say this is our path of the planetary body, and I'm projecting it here also onto the B plane. So this is where the center of the body goes. So the surface of this planetary body will intercept this B plane at this position. So now we have two distances. We have the intercept of the spacecraft following the white trajectory, and we have the intercept of the planetary surface, which is in the blue. So the planetary, this is the surface of the planet. So there is a difference between these. The distance between these two is very, very significant and important to us. Now, G, please.
So this planetary intersection point that we taken, it means that if the planet were to follow the same trajectory as the
no, the planet is already following its own trajectory.
So it's
this is where the planet will intercept this B plane, okay? Because we have to calculate the distance that is required to either impact, use a gravity assist, or get into a planetary probe. Okay? So the distance is very significant for us. So to do that, let's now put some coordinate systems here. We usually put a coordinate system which is called as R and T coordinate system, R and tangential. So this is R and T coordinate system. And this coordinate system will help us determine the magnitude of the distance between the two. So this distance between two V infinities. So let me just project this outwards. So the V infinity here, by the basic geometry of the hyperbola is called, this is the semi-minor axis. That's the basic geometry. So by that extension, by the same extension, the surface, this is called as the semi-major axis of the impact. So we call it BI. So that's the semi-major axis of the impact, exactly the surface. Now very close in magnitude to this is, let's say there's an atmosphere. If you are looking for a probe, so then you should also be interested about what is the atmospheric height around this planet, right? In that case, the same BI will have a corresponding value very close to it, but greater than that will be another semi-major axis, and that is called as the semi-major axis of the atmosphere of the planet. So it's represented by BA. So we have a B, which is the semi-minor axis of the incoming spacecraft. We have BI, which is the semi-minor axis of the exact surface of the planet, and a BA, which is the semi-minor axis corresponding to the atmospheric height. So the idea of a B plane, by solving this B plane actually, which is of course we have seen that this is orthogonal here. So by solving this whole orbit in a B plane makes the orbit becomes two-dimensional. And why it becomes two-dimensional? So if I was checking this planet, for example, the motion of this planet on the surface of the B plane, then it would appear to be as two vertical lines. For example, the planetary spacecraft will appear to be on a two-dimensional plane as this, and that of the planet will appear to be another one like this. So when you map, because this is coming in, okay, so when this is coming in, but this is only possible when you are mapping from a very large distance, mapping from a very large distance. So any variation in the incoming plane, would be accounted for on the surface. So you may not necessarily mean that you may not necessarily have these two planes at 90 degrees in that case, because only then you will be able to map these two surfaces, because it may be coming in at a certain angle. And this is what is happening. Because this plane, the B plane, is orthogonal to an infinite position. So this is primarily orthogonal to an infinite location, but your incoming plane is at an angle. Why? Why was it at an angle? Because if you remember, when we calculated the orbit, let's say that was the Earth and this was Venus, and we had the two orbits which were in two different directions. So the Earth had a orbit in this direction. This was the ecliptic of the Earth, and then there was an orbit of Venus which was at a certain angle to the ecliptic. It was at an angle to the ecliptic, and so we joined that. We said that the spacecraft leaves here will follow a trajectory all the way, and we calculated this triangle. This spherical triangle, we call this as A, we call this as C, we call this as B, if you remember, and this was the angle alpha, and this was IT at the Earth side, and this was IT at the Venusian side, which means that on the Venusian side, when you draw the B plane, this incoming plane will not be orthogonal to it, because this incoming plane will now be at an angle ITV till the spacecraft has exactly reached the surface of the plane. Only at that point it will be in the same plane. So the spacecraft is actually coming down and trying to meet, it is coming down, let's say, at an angle and trying to meet the orbit plane of the target planet at point B. And if you project it, then it will cross underneath this planet. So this is This is the basic concept. So that's why when we look at from the same B plane, we will see that the entire trajectory of the planet and that of the spacecraft can be mapped by these two lines onto the plane, onto the B plane. So the B plane now houses the trajectory in two green colors, the trajectory of the planet and the spacecraft. It houses the position of the satellite, the target planet, and the intercept positions of the spacecraft and the surface of the planet. Yes, please.
So correct me if I am wrong. If we were to take this B plane exactly orthogonal to the planetary, or let's say,
then you will not see this point.
We will see just a line.
Then you will just see 2 points.
Just 2 points.
2 points. You will not see any line. You will see actually, yes, in that sense, you will see a line. Exactly, an elliptical line. Exactly, you will see elliptical.
So right now we are at the inclination that is constantly changing, and so this B plane can be said to be taken onto the spacecraft. Can we say that we are looking from the spacecraft towards that planet?
No, you are looking from an infinite position onto this spacecraft arriving onto the planet. You are standing infinitely far from that place and looking at the arrival of the spacecraft into that plane. And now, because that distance is infinite, you are looking at a position from where the two planes will cross, where the two trajectories will cross. So you create a plane there. Okay. If that plane is if that plane is orthogonal, then it will create a ellipse type on effect. If it is non-orthogonal and it is orthogonal only to an infinite location, then it will create lines. These kind of lines here. Okay. So it depends on how you are placing that orbit, that plane. The objective here is that we need to calculate the B value, the BI, and the BA. So we have 3 things to calculate here. And as I mentioned, that if we were to let this thing project, then how will it look from this position? Let's say I'm on the B plane. So this is what I'm going to calculate. But before I calculate, just look at the three-way positions. For example, this is Venus. This is Venus mapped onto the B plane. So when we have Venus mapped onto the B plane, so I put this Venus, I'm just putting the half of it. Then the incoming spacecraft is at a distance, let's say B from here. That's the position of the spacecraft. And in order to get to this position, the spacecraft will be going through several adjustments. And we call it the course corrections. So those corrections will appear as we mentioned, will appear as a set of concentric ellipses. So this may be the first ellipse, the first correction. Then in order to cross this, there will be another correction, another ellipse will be formed. And finally, we reach the corrected position. So if you were to draw this, then you will find that there the R, that our coordinate system, that was R, will be pointing in this direction. And we have the T, which will be pointing in this direction. So in this way, you can have the incoming spacecraft. So this is your B here. Okay. So this spacecraft can be at any position above or below that. So because remember that this depends on the inclination of the host planet. This depends on the inclination of the host planet. So that is why even if you put this orthogonal, even if you were to put this orthogonal, because this plane is angular to the orthogonal to the ecliptic. This is orthogonal to this plane, which is at angle, and it is also it is in line and in the same plane. Its equator is in the same plane as the ecliptic. So therefore, these lines will invariably appear on this thing because your incoming plane is at an angle. So this is how the lines will appear to exist on this plane. Because now try to imagine that you have a plane and the incoming plane, it is an angle, and the intercept is at 90 degrees. The intercept is at 90 degrees. So any trajectory mapped there will still be mapped as a line onto this plane. So these lines will appear in any generic case where you have a inclined plane attached to the B plane. So the idea is that if we have to adjust this distance between the two planes, let's call it the delta B. So this delta B will determine what kind of a mission we will be performing, and that is why your R vector and the T vector. So the T vector was in this direction. So you can have your incoming spacecraft lower than the planet, because it is coming down, and then it can go down, and then it will create the orbit around this thing, which can be an inclined orbit. So if it is an inclined orbit, so then this will go around this orbit, and the R and the T, which are in the B plane, will be at an angle to the spacecraft's orbit. Okay.
Sir, if we are having on that B plane, we are seeing those the trajectory endpoints as one point, the endpoint which is actually on the B plane. Then why are we depicting them with these ellipses, sir? Why not symmetry?
In order to get to this point, a number of course corrections are introduced. So those corrections, they create a kind of an elliptical motion. So वो elliptical motion हमने इस पे add किया, ठीक है? What we are interested in is getting to this point, which was actually on this B plane.
We are just trying to be at the same inclination as the planet's orbit. Is that it?
Yes.
When we are drawing this ellipse.
Okay. So R and T, they are in the B plane. Okay? They are in the orthogonal plane. But the orbit of the space of the planet can be is possibly this one. ये उसका plane है. So the spacecraft is in the plane of the orbit. Is in the plane of the planet. But the B plane is orthogonal to this plane. ठीक है?
And these ellipses, the ones you've drawn at this point, the T.
These are called as course corrections. In order to make sure that you maintain a B and a delta B is maintained, you have to make the corrections to your course. So every course correction will appear to be a set of ellipses with we call as 3 sigma corrections. So we introduce those 3 sigma corrections, which is standard deviation in the correction data, till you actually home into that exact point.
What is the reason why we need this?
Because you're coming from a very long distance, so you have to make course corrections in between to make sure that you get to the right point. Okay. So orbit, the insertion to the orbit has to be very correct. Okay. Now, in order to calculate this thing, in addition to whatever we have already mentioned, we will the first thing we do is as a matter of process. Once we have the B plane established, so after the B plane, we will do the plane change calculations, and we have already learned what we do in the plane. In order to calculate these values, these variables, we must first do the plane change calculations, and those plane change calculations will give us the ITV, will give us the alpha at the arrival, and it will also give us the V infinity of the spacecraft on its arrival into the planetary body. Okay, so if you can always use the handouts for the hyperbolic orbit. So in order to get the value of B, any B is actually determined directly from any relations, which is RP into, for a hyperbolic orbit, RP into 2 mu of the planet, whatever planet it is, RP into VHE square plus 1. That's your relation for the hyperbolic orbit. We already derived this relation. Now, in order to do, for example, the BI calculation, what will happen? For BI, some corrections will be made. For example, we will change the RP we will change this RP for the radius of Venus. We will change this to the radius of Venus, because then the periapsis, because then we will assume that it's going to impact onto the surface, and therefore we will use the RV value here. The mu will be used as it is. The VHE, instead of VHE, this is at the departure, we will replace this at the arrival. We have V infinity at the arrival. So, we will replace the VHE with V infinity. So, that means since we can calculate the value of RV, that is not a problem. The value of the RV is about 6052, the RV, sorry, this RV, capital RV, is 6052 kilometers for Venus. But what we don't know is what is the value of V infinity here. Just for record purpose, the mu of the planet is that of mu of the Venus, and which is very close to that of the Earth, 32485 8.8 kilometer cube per second square. So, therefore, now we have to find the value of V infinity. This V infinity depends on our arrival at the planet. Yes, and we'll do the same triangle calculation that we did the last time. So, we already knew what so in order to calculate the value of V infinity, we first need to establish the magnitude of ITV. So, let's do that step first. Now, so if you remember, I just recall the old figure here. Yes, this one. So, I am going to just draw this triangle which we used for last time, the calculating from the Earth launch, from the Earth end. That was one corner. The other was the projected corner of Venus, and then there was a node, ascending node, where the ecliptic was crossed by the Venus orbit, projected Venus orbit. So, this triangle was solved last time. So, we are going to use the same triangle because it has departure inclination at one end and arrival inclination at the other end. So, we can very conveniently use that. So, on the arrival end, what will happen is we have for example, this spacecraft coming in, and we also have the planetary orbit. So, the planetary orbit was in this way. So, this was the rightmost corner, the arrival corner, isn't it? This is the center of the planet, for example. So, this this was the arrival velocity of the planet with respect to Sun, and on this side was the arrival velocity of the spacecraft with respect to Sun at the arrival point. And the angle that we had calculated between these two was I on the transfer orbit, ITV. So, it was the transfer orbit, the inclination ITV. Now, just if you want to recall, we had this figure. This big figure is part of that same triangle that we had used. This was the Earth here. There was an intercept N, or we called it the point X, and then this was the intercept with the Venus side. So, this was the trajectory of the traversing trajectory. This was Venus on this end, and this end was ITV. We had A and B and C, and we had an alpha here, and there we had an IT of the Earth. So, what we have done is we are just solving for this corner, and this is the figure representing this small corner. Now, when we solved for this corner, at that time we could use the sine rule, the spherical sine rule could be used. For example, on this triangle we can use that. We have sine of ITV over the sine of A would be equal to sine of alpha over sine of C. And if you remember from those previous calculations, the value of A we had found to be 59.05 degrees. We had determined the value of C to be 132.90. Please check your previous calculations. And we had determined the value of alpha as 176.61 degrees. So, therefore, the unknown ITV can be determined here. So, you will get the value of ITV as sine, arc sine, which will be sine of A, sine of alpha over sine of C, and so your ITV will come out to be 3.975 degrees. This is the inclination on the transfer trajectory that will be required to enter into the Venusian orbit. So this is our first step, which is the determining the plane change. And as you see, so we have the arrival targeting, and we are now solving for the plane change. Now the next step to the plane change was to calculate the V infinity, so that once we have these two parameters, then we can go back and calculate the value of B, the value of BI, and the value of BA. Because to calculate the value of BI, BA, we need the value of V infinity. Okay, so to get the value of V infinity, so the V infinity square at arrival, and what can we use? We use the same kind of, yes, the triangle, the velocity triangle we did the last time. So what kind of a velocity triangle will exist now? So this is Venus. So now I'm actually expanding this figure. I'm expanding this figure into a two-dimensional figure. So this is Venus here, and the trajectory of Venus, for example, that's the trajectory of Venus. Okay, so the local horizon of the Venus is mapped here in this position. That's the in fact, we don't need to put an arrow here. We just need to put a dotted line that's showing the local horizon of Venus, from which what was measured? The flight path angle. And if the blue is the trajectory of Venus, this was the trajectory of Venus around the sun, then this would be the velocity, and this would be the velocity of Venus, V of planet with respect to sun. So this angle between the two would be the flight path angle. This here is the phi flight path angle of Venus with respect to its own local horizon, and it would be measured in the horizontal plane, right? So I am drawing a horizontal plane here. Now ITV degrees below this plane, vertically below this plane, is the position of the spacecraft which is coming in from around so this spacecraft was coming in from behind, and this would be the position of the spacecraft crossing underneath the planet, and the angle would be now measured in a vertical plane. Please refer back to the previous diagram also. We did this in the last class as well. So this is a vertical plane, and this vertical plane follows an angle which is ITV. So this is my IT of Venus, which the spacecraft is following. And then this spacecraft has a velocity vector, is following its own. So this velocity vector is with respect to the center of the Venus is, let's say, going outwards, and this is in the lower plane. Remember, this is in the lower plane with respect to the incoming. So this velocity vector is in the plane, in this plane. So we have two planes.
So this velocity vector is
the velocity vector of the spacecraft with respect to sun at its arrival. Okay, and so what did we have at that time? We would then take the V infinity would be the vector connecting these two. So this will be your V infinity at arrival, and we had a slant angle, and we have a slant angle between the two. So this slant angle would be your arrival alpha. So this slant angle is your arrival alpha, and we can solve this slant angle in a planar triangle, because now the triangle, the velocity vector, the triangle that they are forming is a planar triangle, and you have to get this thing developed for every single scenario. Okay, so now if we take a two-dimensional look of the vectors, then what do we have? We will have this is Venus, for example, here the position of Venus, and there is a flight path angle phi v out of this. So this is phi v, and this is the velocity vector of, so this is velocity vector of the planet with respect to sun coming out of the plane of this paper, and below this at an angular position a distance ITV is the plane of the spacecraft, which is at a certain distance, and that is angularly measured as phi of the spacecraft. So we usually refer to this as, I forgot to mention this figure. So this, in this plane, is your phi. This is the phi of the spacecraft, which is at arrival. So so therefore this phi is the flight path angle of the satellite. So we call this flight path angle of the spacecraft on the transfer trajectory at the arrival. This is exactly how we mentioned the last time also, fly of the spacecraft on the transfer trajectory at the departure. So this is S on the transfer trajectory at arrival. So that's the angle. This means, okay, so this is the angle phi. From here to here is your ITV. So that leaves the red. If you connect these 2 points here, then, and not to forget that this was your velocity of the spacecraft with respect to sun at the arrival. So this will be your V infinity between these 2 points. So this is your V infinity. And the angle corresponding to the slant angle corresponding to this V infinity is your alpha at the arrival. So this is exactly how we constructed the departure triangle as well, or except for the fact that there was a difference between how the angles were measured depending on the position of the sun, earth, because the earth is outer to the Venus and the Venus is inner to the earth. So the direction is on both the angles are measured from the same side. Okay, so V infinity square A, we use the triangle, let's say we call this triangle center of the Venus and A here and a B. So if we solve triangle CV, A and B, so we can get the value by the simple planar cosine rule, which will be V infinity square at arrival will be equal to velocity of the planet with respect to sun square plus the velocity of the spacecraft with respect to sun at arrival square minus 2 VPS VSSA into cos of which angle? Included angle is alpha A, right? So into cos of alpha A. Right. So now we also, to get the angle alpha A, this triangle was used last time. So we don't know this thing, but we do know the VPS, the velocity of the planet with respect to sun. We calculated in the beginning in step number 1 when we were doing the planetary calculations. So at that time we calculated this to be 34.80 kilometers per second. The velocity of the spacecraft with respect to the sun at the arrival we did the last time was 37.57 kilometers per second. So all these values, but what we don't know is this value. So as a result we don't know this alpha as well. So what we can do is we can just put this as 29. So we can use the equation for this here to determine what is the angle, and the equation we used was cos of alpha A was actually cos of ITV into cos, and now because this alpha A relies on the difference between these two angles, so it relies on this side. The previous instance when we were departing, we had alpha on this side, we had this on this side, so the angle was based on the sum of both the angles, isn't it? But here it now relies on the difference between the delta phi's. So therefore that will be the cos of phi of the spacecraft on the transfer trajectory at arrival, spacecraft on the transfer trajectory at arrival minus the phi of the Venus on its own orbit. Now we know these values. Why? We know the value of ITV. We calculated we know the value of ITV. We also know the value of phi STA, which is 3.9407, and we know the fly path angle of V, all calculated in the previous steps, 0.1280, and this was 4.455. So the alpha A would then come out to be about 5.509 degrees. Now once you have the value of alpha A, the V infinity, now we can put this value of alpha A back into this relation here. So it goes back right here. So that will mean that your V infinity would come out to be 4.442 kilometers per second. Okay, once we have the value of V infinity, and this you may ask that you get a calculation of 3.975 here and instead of 4.455. It is because these two calculations were performed on two different ephemerides. So if you follow the previous ephemeride, then you will get a 4.455 right here. Okay, that's the only reason. So you could always ask this question. So I've answered this because I was calculating at two different ephemerides, just checking the difference between the two results. Okay, so there's a small hunt of 0.5 degrees that occurs between on a day-to-day basis. If you change the day, so it will cause a change here. Okay, so this should also go.
You cannot use this one.
You can use this one, no problem. But it will just create a very small variation here. But since we are following the previous calculations were based on 4.455, I guess. So, sorry, that was the ITeV. My bad. That was IT of the Earth. So this is 3.975. Okay.
Should we
Okay.
calculate it again?
No, this is correct. This is calculated with alpha A is calculated with 3.9. My bad of writing that 4.5. I forgot those numbers. There were so many angles. I forgot the numbers for that angles. Okay. The only thing is that sometimes you may get a small variation of 3.975, maybe become 3.98 or 3.976. So don't get worried about that part. Okay. Okay. V infinity is done. We have a very important figure. This is the infinite velocity now available to your spacecraft on its arrival. And we also know the value of alpha A. This is another important angle because this angle will determine how with respect to the position of its previous, because this is past conic. So you have alpha A with which the spacecraft is going to approach at the sphere of influence. This is the alpha A with which the spacecraft is approaching at the sphere of influence and will be looking at the planet for approach.
With
This
respect to that planet's
yes, with respect to that planet's position. This is how it's going to look at the angle, and we're going to draw that triangle. They're going to specific triangles for that.
Why the V infinity is in this case more than the hyperbolic excess? Because we are only having a very small velocity at the very end. So are we? Is there any contribution of the planet's motion?
Exactly.
Sir,
Because you have moved inwards. This is an inner planet. So the moment it is just like coming closer to the Earth. So the moment you are going from outer planet to the inner planet, your velocity will increase. If you are going to an outer planet like Mars, the V infinity would be less than your hyperbolic excess velocity at that time.
sir, this V infinity, this is the velocity with which it's going to fall onto the planet.
Yeah, this is the velocity. This is the velocity that is still available to the spacecraft as it is approaching the planet. And then that planet will impart its own delta V, which is the gravity assist, and then a new velocity will be created for this departure from that place. Okay? This is and by the way, this is the velocity which is with respect to the sun. This is the V infinity that this is carrying with respect to the sun and not with respect to the planet itself. So it's between with respect to the sun's position. Okay.
So what about the direct impact case? is this?
In that case, we will do the BI calculation and set the B value smaller than BI. Set the B value smaller than BI. Okay.
Right now, this is a gravity system.
Yeah, we are solving for the gravity system. Interplanetary कर रहे हैं ना हम. Okay. Next is we still have to calculate those basic items which was B, BI and BA. So now we can
Save the recording.
thank you.